Hello students, welcome to Cbse Tayari. I'm your educator and today we will be studying class 10 science chapter 3, that is metals and non-metals. Let's get started with today's class. To begin with, we will study about the physical properties of both metals and non-metals. What are metals? In the earlier chapters, we have learned examples of metals. For example, those are iron, copper, aluminium, magnesium, sodium, lead, zinc, etc. There are many more. What are these properties? What are the properties that these elements have that they are characterized as metals? Let's learn about those properties. One, that is lustre. What is meant by lustre? Lustre means soft glow. Do metals show this property? Yes. Metals show this property, that is they have a shiny surface. Example will be gold, silver. Hardness, that is whether they are hard, they are soft, what is the nature, what is that metals show. Metals are generally hard. They are hard. For example, Fe, that is iron. State. What is the state of metals? Metals are basically solid. However, there is an exception. Exception is mercury, which is liquid at room temperature. That's why we use mercury in thermometers, and those manually watch thermometers that are used to check temperatures, not the digital ones. In that thermometer, we use mercury because they are liquid at room temperature. The fourth one is malleability. What is meant by malleability? This is a term that we have come across for the first time. So, malleability is the ability to deform under pressure. That is, in simpler words, that whether it can be an element can be beaten down into thin sheets. Whether an element can be beaten down into thin sheets, that is known as malleability. Do metals show this? Yes. They can be beaten down into thin sheets. Example is again gold, silver. The fifth one is ductility. What is meant by ductility? Ductility is the ability to be drawn into a thin wire without breaking. That is thin wire without breaking. Do metals show this property? Yes, metals are ductile. That is, they show this property, that is they can be drawn into thin wire. What are the examples? Examples of this are copper and aluminium. Okay. Now, good conductors of electricity. That is whether they can pass electricity or not. Metals are generally good conductors of electricity. They are good conductors of electricity. Example is again copper and silver. Copper is used in those house wirings. House wires, because they are good conductors of electricity. The seventh one is density. What happens? Metals are basically show higher density. As a result of higher density, metals are also showing higher melting point. We can say that density and melting point are directly proportional. That is, if density is high, melting point is also high. Density high, so melting point will also be high. If density is low, melting point will also be low. The eighth one is sonorous. What do you mean by sonorous? That is the ability to produce sound. What does this mean? This means whether an element when beaten with a hard substance produce sound or not. In case of metals, yes, they are sonorous. Metals are sonorous. And the ninth one is oxides. We have already studied about metallic oxides in chapter 2, and we know metallic oxides are basically basic in nature. Okay? Now let's move forward and learn about the physical properties of nonmetals. Nonmetals. What are the examples of nonmetals? Examples of nonmetals are carbon, sulfur, iodine, oxygen, hydrogen, etc. Let's look into their properties. Number 1, lustre, that is the soft glow. Do nonmetals show this? No, they are basically non-shiny. But there is an exception, that is iodine. Nonmetals are basically non-lustrous, that is they do not show shiny surface, that is they are non-shiny, and there is an exception, that is iodine. Hardness, these are soft. Non-metals are soft. However, here again we have an exception, that is diamond. Diamond is the hardest and this is a non-metal. So this is an exception. State. What are the state of non-metals? Non-metals are basically solid or gas. Okay. However, again there is an exception, that is bromine, that is liquid. In metals we have seen exception, that is mercury, and in non-metals it is bromine. Malleability. Malleability, that is whether it can be drawn into a thin sheet or not. Non-metals do not show this property, that is they are non-malleable. Okay. Ductility. Let's go. Ductility. Ductility is whether they can be drawn into a thin wire or not. Non-metals are non-ductile, that is they again do not show this property. They do not show this property. Number 6 is conductor of heat and electricity. Non-metals are poor conductors. They are poor conductors of electricity. The 7th one, density. We have studied density and melting points are directly proportional, and in non-metals we see the density is less, so the melting point is also less. Similarly, 8th, sonorous, ability to produce sounds. Do non-metals show this property? No, that is they do not produce sounds. And 9th is oxides. We have studied non-metallic oxides are acidic in nature. So let's recapitulate all the physical properties of metals and non-metals and compare that. Okay. First, in case of metals we see lustre. In case of metals, lustre, and non-metals, lustre. Okay. They are lustrous, that is they are shiny. However, non-metals are not. Hardness, they are hard metals. Non-metals are soft. State, they are solid, and there is an exception, mercury. These are solid or gases, and they are bromine, exception. That is, these two are liquid. These two are liquid. Malleable, whether a metal is malleable? Yes, it is. Non-metal? No. Similarly, whether a metal is ductile, yes, metals show ductility, whereas non-metals are not ductile. They do not show the property of ductility. Then we have conductors of electricity. So metals are good conductors, whereas non-metals are poor conductors. Then we have density. So metals are show high density, non-metals show low density, thus high melting point, thus low melting point in non-metals. Okay. Then sonorous. Yes, they show sonorous property, that is they make sound when hidden with a hard substance, whereas non-metals are not sonorous. And the last one is oxides. Metal oxides are basic, however non-metal oxides are acidic. So this is the comparison of all the physical properties. I hope you have understood and you will remember it. So let's move forward and learn about the chemical properties of a metal. What are the chemical properties of metal? How it reacts with under various environments. So how does a metal react with air? Okay. So we can write metals when reacted with oxygen, it will give you what? Yes, metal oxides. It will give you metal oxides. Let's see an example. Here we have copper, and when burned with oxygen, when reacted in the presence of oxygen, it will give you copper oxide. This is a metal oxide. And we have learned metal oxides are basic in nature. However, there are different metals that react differently in the presence of air. Let's see those. Na and potassium, they react vigorously. That is, they catch fire in open places. That is the reason why we always keep these metals immersed in kerosene oil. Then we have aluminium, zinc. These are covered with a layer of oxides, with a thin layer of oxides, because these two, they can undergo oxidation. We have learned about the process of oxidation in chapter 1. So these two elements are covered with a thin layer of oxide so that no further oxidation occurs, because oxidation turns a metal weak, and as a result corrosion occurs. Okay. Now there are exceptions, that is two metals that do not react with air at all. What are those? That are Au and Ag. They do not react with air at all. They do not undergo any reaction. Okay. So these are the different metals and how they react with air. All metals react differently with air. So in case of copper, we will see there is a formation of metal oxides, and these are the different metals, how they react with air. Okay, now let's go forward and learn about how metal reacts with water. How metal reacts with that of water. So when metal and water reacts, there is the production of again what? Metal oxides. However, there is production of hydroxides as well. What are the conditions? How do we know a metal oxide or a hydroxide is formed? See, if a metal is highly reactive, it will form hydroxide. However, if a metal is not that much reactive, is less reactive, it will form metal oxides. We will learn about the reactivity in the reactivity of various metals in the reactivity series in the coming slides. Okay. So let's learn about how metal react with water. So metal will form metal oxides or hydroxides. Let's see an example, that is Na, which is a metal, when reacts with water gives you a metal oxide NaOH. If you remember, in chapter 2 we have seen NaOH is a strong base found in soap. I hope you remember this, and this was in chapter 2. Okay, now there is also a thing which is when metal oxides will react with water, it will form metal hydroxides. Okay, you have to remember this as well. That is, when metal oxides react with water, it produces metal hydroxides. So basically, metals when react with water, they will give you metal oxides or hydroxides, and also a gas is evolved, that is hydrogen. H2 is also produced. Okay, so H2 is also produced. So this equation can be written as Na plus H2O will give you 2NaOH plus H2. Okay, and this equation is not balanced, so we will be balancing this equation. That is, here we have 2 Na, however in the reactant we have 1, however in the product we have 2, and here we have 2 hydrogen and 1 oxygen. However in this case we have 1 and 2, 3, and we have 2, 4, and we have 2. So what we'll do, 2 NaOH plus 2 H2O, that is Na is balanced. Now we have 4. So 4 is also balanced, and O2 is also balanced. So we will write this equation as, I'm writing it here, 2 Na plus 2 H2 will give you 2 NaOH plus H2. This is how a metal will react with that of water. Okay, in this case also we have different metals that react with water in a different way. That is, let's learn about them again. So in case of sodium and potassium, they react with cold water. Magnesium on the other hand will react in hot water. Again, Au and Ag, no reaction. In case of metals that were burnt in presence of air, they did not show any reaction. Similarly, in water also they do not show any reaction. Okay, and aluminium and zinc, as we in the thing in metals when burned with air, we have seen they were coated with a layer of oxides. However, in case of water, they react with steam. Na and sodium and potassium will react with cold water. Magnesium will react with hot water. Aluminium and zinc will react with steam, and Au and Ag do not show any reaction at all. Okay, now let's move forward. There is a term that is known as amphoteric oxides. What is this amphoteric oxides? Amphoteric oxides are metal oxides that react with both acid and base and results in the formation of salt and water. What is it? They will react with both acid plus base to give you salt plus water. Example of this is Al2O3 plus 6HCl, that is a strong acid, will give you a salt, that is AlCl3 plus water. What are this? These are basically metal oxides. Amphoteric oxides, metal oxides, that is we know is basic in nature. They are basic in nature. Okay. Now let's move forward and learn about the chemical properties, that is how metal reacts with that of acid. Further we have learned how metal reacts with air and how metal reacts with water, and now we will learn how metal reacts with acid. Metal, when reacted with dilute acid, what is a dilute acid? Where concentration of acid is less, however the amount of water is more. This is known as a dilute acid, and that will produce salt plus hydrogen. Let's know an example for this, that is Fe, that is a metal, and 2HCl, that is diluted, will give you what? FeCl2, this is a salt and hydrogen. So how metal reacts with acid? When metals, and we have to do it with dilute acid, because metals when reacted with concentrated acid, there is a high exothermic reaction, and we know in exothermic reaction with the production of acid there is a release of high amount of heat. So we do not take concentrated because the reaction is highly exothermic. So we will not take in consideration of concentrated acid. Metals are always reacted with dilute acid to give you salt plus hydrogen. Example will be Fe, that is iron, plus 2HCl, that is in dilute form, will give you FeCl2, that is a salt and hydrogen. Okay. And now let's learn about how metal reacts with solution of other metal salts. In this case we are seeing that is metal A will, when reacted with salt solution of B, there is a production of salt solution of A plus metal B. Can you tell me what type of a reaction is this? Yes, you are right. This is an example of a displacement reaction. We have learned about this in chapter 1. That is, here metal A and metal B were there as reactants. However, in the product, metal B is replaced by metal A and metal B is replaced by metal A is replaced by metal B. Let's recapitulate. That is, metal A plus salt solution B, these two were the reactants, and what is the product? We get salt solution of A, that is from the metal A, it is gone to salt solution of B, has been transferred into salt solution of A, and metal A has been transformed into metal B. And this is an example of a displacement reaction. Let's learn about this with the help of a example. Let's take Fe again, that is iron, and react it with the solution CuSO4. This will give you FeSO4, that is a salt, plus Cu. In this case, we see, what do we see? We see that Fe has completely replaced Cu from CuSO4 solution and transformed into FeSO4, and Cu has been separated. Why does this happen? Because Fe is more reactive as compared to copper. We will learn about the reactivity series in the coming slide. Okay, we will say this is a displacement reaction because the Fe has completely replaced the copper from copper solution and transformed into FeSO4, and the copper is left alone as Cu. Let's move forward. This is the reactivity series. What is a reactivity series? The reactivity series is a list of metals that is arranged in the order of their descending activities. That is, it is a series which arranges metals in the order of their descending activities. That is, as we have seen Fe replacing CuSO4. Why does this occur? Because Fe is more reactive than copper. As a result, it can easily replace copper. Okay, now let's see what this series is. In this series, on the top, from the top to bottom, it is a series where the highly reactives are placed on the top and the less reactives are placed in the bottom. So we see potassium is the most highly reactive metal, followed by sodium, then lithium, then barium, then strontium, calcium, magnesium, zinc, chromium, iron. See, iron is here and copper is here. So copper is iron is more reactive and copper is less reactive. So in the displacement reaction, copper could easily be replaced by that of iron, because iron had more reactivity and copper is less reactive. Students, you have to remember this at least, because this is how a metal reacts. So you have to know which metal is, how it reacts, which is highly reactive, which is moderately reactive, and which is least reactive, because this is a question that gets asked, at least one question gets asked from this topic every year. Now let's go forward and learn how do metals react. Metals and non-metals react. Okay, first of all, we have to know why does this metals and non-metals actually taking part in a reaction, or why do they react? They react because the reactivity of an element is because they have the tendency to attain to fill their valence shells. That is, they have the tendency to completely fill their valence shells. Okay. Now, what is this filling of valence shells? We will learn. Okay. Let's see. In case of sodium, they have the atomic number of 11. Okay. Now, this is the electronic configuration, that is 281. That is, this shell has only one atom, so a one electron. So what this metal will do, what this sodium will do, it will try to give this away. Metal will try to lose it to form cation. They will lose, metal basically lose to form cation, and non-metals will gain. They will gain to form anions. Why do they lose and gain? Because they want to attain valence shells. That is, they want to attain filled valence shells. If this is not filled, however, this is filled. So if they give it away, this becomes stable because it has a filled valence shell, and this is the tendency of all metals and non-metals to fill their valence shells. So let's recapitulate. Metals will give away in electrons in the form of cations. Similarly, non-metals will gain. They will gain from these metals and they will form cations. Okay. Now let's see an example. See, for this example, we are taking formation of sodium chloride. Sodium chloride, sodium is Na. We have learned its electronic configuration is 281, and Cl, that is chloride, its electronic configuration is 287, that is 17, and this is 11. Okay, so we know this is a metal and this chloride is a non-metal. So let's see how they tend to lose electrons to attend a built valence shells. Okay, see Na, what it will do? It will lose. Na has 281. So what it will do? It will lose an electron and get a positive charge. It loses an electron and the electronic configuration becomes 2 and 8, and it has lost an electron. And this electron gets accepted by Cl, and this accepts this electron and it becomes Cl minus. What was the initial configuration of Cl? That is 287, and now it has become 288. So this is a valence shell, this is also a valence shell. This is how the formation of sodium chloride occurs, and this is how we can say that a metal and non-metal reacts. And they basically react due to two reasons as already mentioned. First is to attend filled valence shell, and the second one is, yes, you are right, lose and gain. Okay, lose, and they will lose electron, and this will gain electron. They will lose to form cation and they will gain anion. Okay, so this is the same example, that is formation of sodium chloride. See, it has, this is the electronic configuration, it has lost, that is sodium cation, and it has gained, so sodium anion. Okay, now let's go forward. What are the properties of a ionic compound? Properties of a ionic compound. Okay, first one is physical state, physical nature or physical state. These are basically solid and hard. They are solid and hard, and they have high melting point and high boiling point. That is, they have high melting point and high boiling point. What are these? These are properties of ionic compounds. And the third one is conduction of electricity. They conduct electricity, ionic compounds conduct electricity only in the molten state, but they do not conduct any electricity in solid state. What are the properties? Let's recapitulate again. Ionic compounds can be shown three properties. First is the physical nature, that is, they are solid and hard. The second one is metal ring melting and boiling point, that is MP is high, melting point is high, and boiling point is also high. And conduction of electricity is, they can conduct electricity only in the molten state and not in the solid state. Okay, I hope up to this the slides are clear. Up to this you have understood all the topics. Let's go forward. Now, since we have studied about metals, from where do these metals where do we get these metals? This metal has to be coming from somewhere. So, from where does this metals occur? Occurrence of metal. This is our next topic in the chapter. Metals basically occurs in three forms. First is the mineral, second is the ore, and the third is the gunk. Now, what are these three? Let's understand one by one. Metals, minerals. What are minerals? Metals, we derive metals from minerals, we derive metals from ores, and also gunk. Now, what are these? Metals are basically compounds that occur naturally in the earth's crust. What are minerals? Minerals are compounds that occur naturally in earth crust. Okay. Now ores. What are ores? See, minerals that have metals are known as ores. They are minerals that have metals and we can easily extract them. These are minerals that have metals. Mineral with metals are known as ores and we can easily extract them. What are gunk? Gunk is ores that have ores, that is basically minerals that have metals and that can be easily extracted. This ores also has gunk. That is, gunk is basically impurities that are present in an ore. Okay, so we can say that metals occur in three forms. That is, first is mineral, second is ore, and third is gunk. Minerals are naturally found in earth crust. Ores are minerals that have metals and can be easily extracted, and gunks are present impurities in that ore. Okay. Now we will see how these metals are extracted. How these metals are extracted from ores. We have learned ores are minerals that already have metals and we can easily extract them. Okay, there are three steps. First is the enrichment of ore, the second one is the extraction of metal, and third one is the refining of metal. What is this enrichment of ore, then the extraction of metals, and then the refining of metals? Let's study about it one by one. What is enrichment of ore? Okay, enrichment of ore is basically extraction. Okay, that is, we take the ore and then extract it. How is this done? This is done by leaching. These are basically methods. Okay, enrichment of ores are carried out by various methods and the methods are listed here. That is leaching, magnetic separation, then froth flotation. Enrichment of ores are done by these three processes. What do you mean by leaching? Ores are soluble. Here we make ores soluble and the gunk becomes insoluble. As a result, we can separate the ore. Enrichment is separation of ore from the gunk, because ores also contain gunks, that are impurities that are not needed. So we carry out various methods so this gunk can be separated. First is the leaching, where we make the ore soluble and then we make the gunk insoluble. As a result, the insoluble one will settle down and the one that is the insoluble gunk will settle down. This is the container. Gunk settle down and the upper part we get the ore. Okay. Second is the magnetic separation. As the name suggests, it is the use of magnets. And the third one is flotation, that is separation of hydrophobic and hydrophilic materials. Hydrophobic means that fear water, and hydrophilic means materials that love water. Hydrophobic is water fearing, hydrophilic is water loving, and with this we separate ZnS, CuS. Okay. And the second process we have learned about enrichment of ore. This is done by three methods. That is, enrichment of ore is basically removal of gunk. We will separate gunk to get the pure ore. Okay, from this ores we have to extract metals. Okay, now let's go forward and learn about the extraction of metals. See, Extraction of metals. Now we have learned in the reactivity series that metals have least reactivity, medium reactivity and high reactivity. Now we have to extract metals in the form from least reactive as well, from medium reactive and high reactive. That is, we have to extract metals that are least reactive, that is mediumly reactive and that is highly reactive, and all these processes are different from one another. That is, we cannot separate a highly reactive metal with the process of that of least reactive metals. Okay, so let's learn about how metals with least reactivity are separated. First, in this case, oxide of these minerals, what are they done? They are reduced by heating, and for example, we can say they are done by heating. For examples, we can say is, we can take Hg, and this is extracted from HgS, that is known as cinnabar. How it is done? It is done that we extract Hg from HgS, that is known as cinnabar, and these are sulfide ores. How do we do that? We do this by let's see this, Hg plus 3O2, then we will have heat and this will give you 2HgO plus 2SO2. As a result, again this one we will react 2HgO and give heat and we will get 2Hg plus O2. Okay, this is how we get less metals that are less reactive. Okay, we give heat, as a result there is a formation of HgO, then this again is heated to finally get the metal. Okay, let's go forward and learn about how metals with medium reactivity is extracted. Also, this process that we used is known as roasting. Roasting is giving heat, and then we get the metal and then we further purify the metal. Purification is the final step, refining. Okay, this process where we use sulfide ores and give heat to get the metal, it is occurred in case of metals with least reactivity, that are at the bottom of the reactivity series. Similarly, let's learn about extraction of metals that are middle in the reactivity series. These metals are easier to obtain. Okay, and these metals are easier to obtain, and they are in the form of, they are in two forms, that is sulfide ores, however, and here carbonate ores. Okay, carbonate ores and sulfide ores. What do we do? Again, what do we do is roasting, that is giving heat. Okay, and where it is done? It is done in case of sulfide ores, as seen in with least reactivity. Same we do again here. And what is this? This roasting is done because to convert into metal oxides. Why do we do it? We do this to convert it into metal oxide. As we have already seen, we convert it into a metal oxide and again we give heat and we get metal. Similarly, again sulfide ores are heated to get metal oxides, and from this metal oxide we will again extract the metals. Okay, and in carbonate ores, what do? We again heat this. However, in this sulfide ores, we give oxygen in the presence of air. This process occurs. However, in case of carbonate ores, there is no oxygen or very least oxygen. Okay, this occurs. This calcination process occurs in the absence or limited oxygen. Okay, let's see an example for this. We'll see ZnCO3 will give you ZnO, which is a metal oxide, and CO2, that is carbon dioxide. Okay. After this, both we got from this both processes we will get metal oxides. From this metal oxides we will have to extract the metal. How it is done? It is done by reduction to metal. That is, what is reduction? We have already studied. Removal of O2 is known as the reduction. It is known as the reduction process. Now there are various reduction agents. For example, CO and H2O. These are reduction agents. Now let's see a example here. Okay, of this, how a metal oxide, for example ZnO, and we react it with C, that is a reducing agent. What we will get? Zn plus CO, and we get the metal. This is how we do metal with medium reactivity. This is how metals are extracted. First is for carbonate ores we use it, and for sulfide ores we use it. For carbonates we use calcination, and for sulfide we use roasting. Okay, then what we do? We get oxides of metals, that is metal oxides. Then we reduce, that is removal of O2 of oxygen with the help of reducing agents, and we get the metal. Okay. Now there is the third type, that is metals that are show high reactivity. What occurs in this case? In this case, what we do is we directly do electrolysis of the molten ore. That is, the ore is first molten, it is melted, and then electrolysis. Electrolysis is passage of electricity. Okay, for we use this, we can say example is NaCl. For extraction of Na we can do, because Na we know is highly reactive. So in this case what we will do? We will take for example, we will set up, here is the anode, cathode, then we will give electricity. Okay, and the metals will deposit at the, when electricity is given, the metals will go and deposit at the cathode, whereas at the anode we will get non-metals. Okay, this is how NaCl, from NaCl we can get Na. That is, when electricity is passed, metals will go and bind to that of the cathode, whereas non-metals will go and deposit in the anode. Okay, the third step is refining of metals. Refining of metals is basically done by electrolysis, that is passage of electricity. Okay, electrolytic refining. Many metals such as copper, zinc, tin, nickel, silver, gold are refined electrolytically. In this process, impure metals is made the anode, and a thin strip of pure metal is made in the cathode. What is it? Impure metals will be in the anode, and the pure metals will be made in the cathode, and the solution of metal salt is used as electrolyte. What we use as electrolyte? We use the metal salt. On passing the current through the electrolyte, the pure metal from anode dissolves into the electrolyte. What was the electrolyte? The electrolyte was the metal salt. An equivalent amount of pure metals from the electrolyte is deposited on the cathode. The soluble impurities go into the solution, whereas the insoluble impurities settle down at the bottom of the anode and are known as anode mud. That is, the soluble impurities will go into the solution, whereas the insoluble impurities will settle down at the bottom of the anode, and it is known as anode mud. Refining of metals is basically done by electrolysis, and this is the electrolyte refining process. Okay, I hope this is clear up to here. Now let's move forward. Now next topic that is discussed is corrosion. We have also learned about it in chapter 1. Again, let's recapitulate what is a corrosion. A corrosion is a metal corroded when exposed to moist air for longer period. That is, metal corroded when exposed to air for long period of time. Example will be silver articles become black when exposed to air. This is because it reacts with sulfur in the air to form a coating of silver sulfide. Okay, that is, silver in the presence of air will turn black because it is reacting with that of sulfur in the air to form silver sulfide. Okay, similarly, iron when exposed to moist air for a long time, they become a black brown flaky substance that is known as rust. We have seen that iron nail, if exposed to humid atmosphere, there is rusting. Why? Because corrosion is taking place. Corrosion is when a metal becomes corroded when exposed to air for a longer period of time. So, we should prevent this corrosion, because in corrosion the metal will become what? The metal becomes, in case of corrosion, the metal becomes weak. So this needs to be prevented. What are the ways we can prevent? The rusting of iron can be prevented by painting, oiling, greasing, galvanizing. What is galvanizing? Galvanizing, chrome plating, anodizing, or making alloy. What do you mean by galvanizing? Galvanizing and anodizing is almost similar. Okay, so let's learn about galvanization, and in turn we will also learn about anodizing. Okay, what is galvanizing? Galvanizing is protecting steel and iron from rusting by coating them with a thin layer of zinc. Here what do? We prevent the rusting of iron and steel by coating them with a thin layer of zinc. Okay, and similarly in anodizing what we do? We again prevent the rusting, and here we coat it with a thin layer of aluminium, Al. Okay, so in galvanizing we use zinc, and in anodizing we use aluminium. Similarly, we can also prevent corrosion with the help of what? Making alloy. What is a making of alloy? Alloy is basically a homogeneous mixture of two or more metals, or a metal and a non-metal. What is an alloy? It is a mixture of two or more metals. It is a mixture of two or more metals, or one metal plus one non-metal. This is what is known as an alloy. Example is iron. Since it, when exposed to humid atmosphere, it undergoes rusting. To prevent rusting, iron is made with a mixture of carbon in the percentage of 0.05%. This is known as an alloy. Okay, another example is brass. How is brass made? It is made with copper and zinc. That is mixture of two metals or non-metals to form alloy. What are these alloys? Alloys are a mixture of two or more metals, or one metal and one non-metal, and it is known as alloy. Okay. With this, we come to the end of the chapter. In today's chapter, we had learned about metals, non-metals. physical properties, chemical properties, reactivity series, and we have learned about electronic configuration. We have learned about extraction of metals, and finally we have learned about corrosion and then prevention. Hope you have understood all the topics that were discussed. With this we come to end of the chapter. Thank you so much for joining.